Okay, hello guys. This video is on waves. I'm hoping you're going to go ahead and take notes on the slides. It's what I wanted to do in class on Monday, but I didn't get to. So I'm going to give you a few seconds at the end of each slide to pause it and copy down the pertinent information. And I would like to look at your notes in class. So I'm going to move on in three, two, one. Okay. If you let me put the video back on. If you look here, what you can see is a wave machine I actually made last year, and it's just a bunch of duct tape with a whole bunch of little kebab skewers and sweeties like gummy bear type candies on the end. And if you just lift it up and take it down, you're going to see that it creates a lovely little wave that moves all the way down. Well, this is a great little machine because to me, shows three main features of a wave. Number one, I did not mean to skip ahead. And number one, the key feature is that a wave moves energy from one point to another. Clearly, if I lift up the kebab skewer and down, I'm giving it kinetic energy, right? And if I lift this one here, for example, I lift it up and down, eventually that kinetic energy works down to here. So it is a way of transferring energy. It has to be through a medium. There has to be something for it to move through. And in this case, it is this curious tape and gummy bear situation of obscure. So it needs to have a medium. And the other thing is, go ahead, just pick one gummy bear, and I'll play the video again. Go ahead, watch one little gummy bear, and you're going to see, I'm just looking at this one here, the yellow one. It goes up and it goes down. It goes down and it goes up. But the fact of the matter is, the individual gummy bears do not move down the waves. They just vibrate up and down, but still the wave moves down the tape. So the notes here is a wave. A wave is a way of transporting energy from one point to another through a medium with no transportation of matter, meaning that the gummy bears actually return to their original position. It's just the energy moves through the wave. I'm going to change slides in three, two, one. Right here, you have the features of a wave. You don't need to look at me while you look at this. Just so you know, the top of the wave is called a crest. I sometimes call it a peak. I think that might be an English American thing, I'm not sure. Trough is at the bottom. I always think of it like a pig's trough, you know, what a pig drinks water out of or eats food out of. Amplitude is a distance from the baseline to the highest point of the wave. In that gummy bear wave, it would be from its equilibrium position where it wasn't moving, and then it twisted up. That would be the amplitude right there. And the other features are wavelength, which is a distance from 2 points on the wave. I just put wave height down for the surfers amongst us because surfers tend to look at the distance from the bottom to the top, but in physics we don't really use wave height. Okay, if you can jot that down, changing slides in three, two, one. Wave velocity, real simple. Wave velocity is the same as any type of velocity. It is just a change in displacement over change in time. There's no smoke and mirrors here. It's just the same old velocity, how quickly it moves, basically, how quickly it changes position. So you can jot that down. You don't have to. It's stuff we've talked about before, but it's going to be the same unit, meters per second. And being a velocity, it is a vector because it is going in a specific direction. And I'm going to go straight on to the for example, this one, it measured out to be about 5 meters long. What would be the velocity of this wave? The easiest way to do it is just time from here to when it gets there and do change in position, 4.8 meters divided by whatever time you got. You don't have to do that, but I'm just trying to prove the point that we're going to measure a wave's velocity the same way we measure any velocity. But there are other ways we can do that, which I'll get to in the next slide. And I'm going to change slides in three, two, one. Okay, I just want to show you a quick video I took with my cell phone. It's of a wave I made with a spring, and it's a long spring. It's not quite a slinky, it's fairly narrow, but I just tied off one end because I was planning and I was on my own. But I want to show you the two different types of waves. So let's show you the first one. I think I did it twice. You can see the wave go down. Can I pause it? There we go. These little white bits, they're just bits from a styrofoam cup I put on just so you can try and look at one part of the wave. But that first type of wave is called a transverse wave. The actual individual coils of the spring go side to side while the spring, the wave moves along. The energy in the spring moves along. They move side to side compared to the general direction of travel. Now, the other type of wave I'm going to show you on the video, it's very hard to see, so that's why I put these white bits on. Just see if you can watch the white bits, see what happens to them. What I actually did was I pushed the wave forward and then pulled it back. And let me see if I can just do this. I pushed the wave forward and back, and you can see the white bit. Oh, yeah. What did I press? Go away, go away. There we go. The actual white bit of styrofoam was vibrating back and forth in the direction that the wave was traveling. That's called a longitudinal wave. The individual particles go back and forth in the direction of travel. I've got 2 more slides on this, so I'm just going to move straight onto them. Transverse waves, the particles oscillate perpendicular in the direction of the wave's motion. A good example is just a piece of string. If I move the string up and down, the wave is going to go in that direction. But the individual particles are moving perpendicular 90 degrees to the direction of the wave. They could, of course, also go side to side if you want to think of it that way. But ultimately, they're moving 90 degrees from the direction of the energy flow, the direction of the wave. That's a transverse wave. I'm going to move on to longitudinal wave in 3 seconds. 2, 1. Longitudinal waves, the particles actually go back and forth in the general direction of the wave. So this individual part of the spring here will, at one stage, well, let's say this part here will move up to compress it out, and then it will stretch backwards to stretch it out, which actually leaves us some new terminology we need to know. Compression, which is where the wave is compressed. Rarefaction, which is where the wave is stretched out. And the amplitude is really just a measure of how squashed together that compression is. That's very hard to measure. We're not going to deal too much with that. Let me just quickly mention examples. Sound is a longitudinal wave because I am, as I'm speaking to you now, I am literally compressing the air with my voice box and opening it up, compressing it, opening it up. So as the sound is coming out, it is compressing against the air next to it, and then that's compressing next to the air next to that, and so on and so forth. Other longitudinal waves are the P waves in earthquakes, where you have an earthquake and the ground literally compresses and stretches out. I'm going to change slides in 3 seconds, and I may stop the video and give you a new one depending on what the next slide is. So we'll see how we go. Yeah, me again. Right on. I'm going to make another video for the next little section. So there's going to be a whole other video about the same length I would like you to watch. So I'll see you in that video. Thank you.